Today I want to talk about the inverse trigonometric functions. But before I get there, I want to do a review of just inverse functions in general, some interesting examples to look at. And as usual, I know that you can skip parts. I'm going to put the chapters in the video, but I would much prefer if you leave it on, at least in the background. I know it's a review. You already know about what inverse functions are. You wouldn't be looking for inverse trigonometric functions if you didn't. But there are some specific things that I want to point your attention to, so that's why I'm going to put the review in the beginning of the video. And most of it is parts from an older video that I had already posted, which was also about interesting examples of inverse functions, but there was nothing trigonometric in that video. So let's begin with the review. But in order to sketch the inverse of a function whose graph you already have, what you have to do is to look at the line y equals x, which I'm putting here in gray in the picture. And then what you're going to want to draw is the reflection of the red graph over this y equals x line. Because when you have the graph of the f of x function, they are points of the form xy. Obviously, the x coordinate is horizontal and the y coordinate is vertical. That the inverse function switches the role of x and y. So every point xy in the red graph is going to have a corresponding point yx in the green graph. So for example, this y-intercept here is going to become an x-intercept here. And this x-intercept here is going to become a y-intercept here. Also interesting points are the points where the graph of f of x crosses the y equals x line, because on those points, if you switch y and x, nothing happens because they are the same number. They are in the line y equals x. So those points actually belong to both graphs. The green graph is going to be going through here as well. And for all other points, I just want to do this visually, really as drawing a reflection. Graphically, I think that this is easier when the function is closer to the y equals x line. So I tend to start here because this bit is easier to draw. And then I just go from there. And also here is kind of easy because it's the point where they are both together. So now I have to reach the other point. And then from this point, I have to connect to the other point, getting closer to the line where the red one also gets closer. And then here you see that it gets a little bit farther away. So I am also going to go a little bit farther away, just trying to make it look like a reflection. The inverse function is switching x and y. So everything that was x becomes y and vice versa. And there are some consequences of that switching of x and y. For example, we've already mentioned in the previous example that a y-intercept is going to become an x-intercept and vice versa. That's kind of obvious because I'm switching x and y, so literally the x-intercept becomes the y-intercept. But other things can be less obvious. For example, if I start with an exponential function here, this is my f of x, and now I'm going to sketch the inverse function to that. So I need my y equals x line here to reflect over. And I'm going to switch the y-intercept with an x-intercept. I'm going to get closer to the line here as the red one does, and then I'm going to go farther away again over there like I was talking about in the previous example. But I am switching everything x for everything y. So x is horizontal and y is vertical, which means that I am switching everything horizontal for everything vertical, and vice versa. But this red function here has a horizontal asymptote, which means that the blue one is going to have a vertical asymptote. The equation of the horizontal asymptote of the red one was y equals 0. And so I am switching x and y, right? So the equation of the vertical asymptote of the blue function is x equals 0. Of course, if you already know that I am talking about exponential function here, of course, this is a logarithmic function down in the other one. That's where the vertical asymptote for the logarithmic functions comes from. It's from the fact that it's the inverse function of something that has a horizontal asymptote. But another interesting thing that also switches x and y in not as immediately obvious a way is that when you talk about the domain of a function, that is all the possible values of x. And when you talk about the range of a function, that is all the possible values of y. So domain and range also has to be switched when you're doing inverse functions, which is why the domain of an exponential function is all real numbers and the range of the logarithmic function is all real numbers, but the range of the exponential function is only the positive numbers, which means that the domain of the logarithmic function is just the positive numbers. That's where that comes from as well. Also worth noting at this point is that not every function f of x that I could have put here in the exercise would have an inverse function. In other words, not every function is invertible. An invertible function is one that has an inverse function. And the thing is that when you draw the reflection, the green thing that I drew here still wants to be a function. And in order for a graph to be a function, it needs to pass the vertical line test. And this one does. Every vertical line that I put here in the graph, you see it's only crossing my green function once. But the way that I could have seen already in the red function that that was going to work is by looking at horizontal lines. Because look, I am switching everything horizontal with everything vertical. So if my blue function is going to pass the vertical line test, then I need my original red function to pass a horizontal line test. And the exponential function certainly does pass that test, as does my previous example. Look, my red function here also passes a horizontal line test, which means that once I reflect it over the y equals x line, the new function, the green one, will pass the vertical line test, so it is a function. So it is the inverse function of the red one, and the red one is invertible. Now, the only way for a function to not pass the horizontal line test and therefore to not be an invertible function is if once it crosses a particular horizontal line, it comes back down and crosses it again. This doesn't stop the function itself from being a function because it is still passing vertical line test here as it goes up and down, but because it went up and down, it's crossing the horizontal line multiple times. So if I try to invert that, then I would get a green function that is going to the left and to the right, something like this. Look, this is not a function. This doesn't pass the vertical line test because the red one did not pass the horizontal line test. So the moral of the story is, in order for a function to be invertible, it can't have any local minimum or local maximum, because when you reflect that, it would make something that goes to the left and to the right, and a function cannot do that. Now, what is the simplest kind of function that you can think of that has a turning point? That would be a quadratic function, of course, and I am going to show you that example. But before I do, let me point out something else that was not in that older video that we're watching. I want to look at what happens when you have a function and its inverse function, and you do a composition of one inside of the other. So I have f of x as my inside function here, and f of x is y. So I put that inside of the function, but now I have f inverse of y, and that is just x. So what we're getting here is that the function and the inverse function, they cancel each other out, which makes sense because that's what inverse function means, right? Whatever the function originally was doing, taking this number into that number, the inverse function is coming the other way around. It's coming back to the original number. So of course the composite function is just going to be x, because it's from where I started, a number x, that's exactly where I came back to. And it works the other way around as well, if you put the inverse function as the inside of the composition and the original function on the outside. I just don't want to get confused with the x's and y's now, so let me change the order of the letters here. I'm going to write it as f of y equals x and f inverse of x equals y. So what do I have now? F inverse of x is just y. And this f of y here is the same as x. So again, a composition that became just the function y equals x. The only thing that could possibly go wrong here is if you have some kind of domain issue. Because when you put a function inside of another function, then whatever comes out of the first function is what's going to be going into the other one. So you have to look at the domains. In the example of the exponential function that we were just looking at in the old video, the 2 to the power of x function doesn't have any domain restriction. It's just all real numbers can go into that function and be the exponent of the 2. So when you have that as the inside function, then that is the domain of your composite function as well. Anything can go in there and then become a 2 to the power of x, but then that's going to be going into the f inverse function, which was a log base 2. So it's becoming a log base 2 of 2 to the power of x. And then we know by our properties of logarithms that those things cancel out, and the answer is just x. If you do it the other way around, then now on the inside you have the inverse function, which was the logarithmic function, but the domain of the logarithmic function is not everybody. Now it's just the positive real numbers. So you can't have a negative number going into this composition. But whatever does go in there gets into the f function, which is 2 to the power of x. So it becomes the exponent of the 2. And again, those things cancel out, and the answer is just x. When we look at the graphs of these functions, then we can confirm what we were saying, because here, by putting the exponential inside and the logarithmic outside, all we're getting is the y equals x function, which is this beautiful diagonal line, because everything canceled out. But then if we do it the other way around, with the logarithm on the exponent of a 2, then the x needs to go through the logarithm first. And that has a domain restriction, which only allows for positive numbers. So when you graph it this way, it is still just the line y equals x, but it is not the whole line y equals x. It's just the positive side of it. And this kind of thing will work for any pair of inverse functions. When you compose one inside of the other, then the answer is just going to be the line y equals x, because one operation is canceling out the other one. And then maybe it's just going to be one part of that line due to domain problems. One example that doesn't have any problems is the x to the power of 3 and its inverse, the cubic root of x, because both of these functions have as their domain all of the real numbers. You can see here that putting the cubic root inside of the x to the power of 3 cancels out, and the answer is x. And the same is true when you do it the other way around. The x to the power of 3 is now inside of the cubic root. Those things also cancel out to have the answer be just x. But in this case, there is no domain issue either way. You can put the cubic root inside, or you can put the cubic root outside. And in both cases, you just get as the composition the line y equals x. Okay, so now let's go look at the quadratic function example. How can we think of inverse functions of this function since it doesn't pass the horizontal line test and is therefore not an invertible function? Well, we can begin by doing the graphical part. So by coincidence, the y-intercept and one of the x-intercepts are the same. So that's going to stay here. But we do have two x-intercepts. So we want to mark two y-intercepts right there. The vertex is also an interesting point to mark precisely. So let's put it at -1 and 2. Now let's attempt to connect the dots. And clearly the green thing does not pass the vertical line test. It is not a function. But you know what I'm going to do? I'm just going to paint one part of that function in a different color. I'm going to paint it blue. And now I don't have two, I have three functions in this graph. I have the red function, which is the quadratic. I have the green function and the blue function. So the thing is that the red function isn't invertible if you look at the whole red function. But if you just look at half of it, then that half, if it's adequately chosen, then in that half you don't have the turning point, which is the problem for a function to be invertible. So I'm just going to paint the vertex here, and everything to the right of the vertex, I am going to paint orange. And now I have four functions. Let's talk about this domain restriction that just happens. The red function is that quadratic for x less than 2. And the orange function has the same expression, but the domain is different. It's x bigger or equal than 2. Now I want to do the green and the blue one. Let's try to do this in the algebraic way. So we have y equals x squared minus 4x plus 3. In principle, this works for both of the functions. I'm not going to have to do the same calculation twice. But now that I am going to invert algebraically, the next thing that I need to do is to switch this y for an x. This is a y, and this is also a y. And now the next step is to isolate y in this equation, in something that is a quadratic equation for y. And now we are going to use the quadratic formula, of course, because that is how we handle quadratic equations. We just have to be sure we know what a, b, and c are in the formula. Well, a is 1 because there is nothing multiplying the y squared here. B is this negative 4. And c is 3 minus x. So let's plug all of that into the quadratic formula. A is 1, so it doesn't need to be here and it doesn't need to be there. Now b is negative 4. The part that people can get confused about is the c, because the c is 3 minus x. So this thing that was reading 4c is now going to read 4 times 3 minus x. This one's going to disappear. This one's going to become a 2. And 4 minus 3 is 1. So that's my final answer. Let me just write it down prettier here. 2 plus or minus the square root of x plus 1. First of all, something with a plus or minus in the middle can't be the expression of a function, because what is plus or minus? Is it plus or is it minus, right? A function can only have one answer. That's actually the whole point of the vertical line test. But the thing is that, remember, I wasn't trying to do this algebraic exercise in order to come up with one function. I was trying to do it to come up with two functions, which is the blue one and the green one. So what's happening here is that the plus is the blue function and the minus is the green function. Now, how do I know which one is which? Is just because plus goes up and minus goes down. And look, the green function is going down, the blue function is going up. So the blue is the plus and the green is the minus. Well, the blue is the inverse of the orange. So that is going to be the G inverse function, which is going to be 2 plus the square root of x plus 1. And then the green function, which is the inverse of the red function, that is going to be the F inverse function, which is 2 minus the square root of x plus 1. And notice how, in terms of the domain of these inverse functions, it's all making sense as well, because the domain restriction that we have here is that we can't take the square root of a negative number. So we need to have x plus 1 bigger or equal than 0 for the domain of both of the inverse functions. That means that x is bigger or equal than negative 1, which is exactly what we see in the picture up there. The blue and the green functions only need a domain starting at negative 1, because that is the coordinate of the point. That is the reflection of the vertex of the original parabola. So when we were working with that quadratic function example, I said that the 2 plus the square root would be the top part of the inverse and the 2 minus square root would be the bottom, because I'm following this convention that square root of something means a positive number, right? And that is reflected in this picture as well, in which the purple function is just square root of x. It is not the example that we were just doing. And not surprisingly, it is a function that has a domain only positive numbers, and then the range is also only the positive numbers. So when you compare that to the exponential and logarithmic example that we were doing first, you expect that when you put the square root of x as the inside function of the composition, and the x squared on the outside function, you know that they're going to cancel out, but if the square root is inside, then the domain of that resulting composition is only going to be the positive numbers, because those are the only ones that can go in this purple function here. And that is exactly what we see. We see a part of the y equals x line, but only the positive part for all of the same reasons that we were talking about before. However, when we use the x squared as the inside part of the composition, which is this green function here, that doesn't have a domain restriction. So any number can go into x squared and then into the square root function outside in that order. So what do you think is going to happen when I show this function? Is that surprising? Now it's not just a part of the y equals x line. Now there is something else happening on the negative side. There's something there. The domain of this p function, which is the composition, is all real numbers. But it's not canceling out in the same obvious way as all of the other examples were before, because the range of x squared is only positive numbers. So when you put a positive number into the x, you are looking at this side of the quadratic, and then the answer is a positive number. That positive number is part of the domain of the square root function, so that is what you're putting in this function here, and you're getting as an answer, again, a positive number because it is above the axis. But if you're putting a negative number in the x to go through that x squared function, then you're looking at the other side of the quadratic, in which, again, the number that comes out is positive because it is above the axis. But then when you go and you put that number inside of the square root, you are looking at the same square root of x function that you were before, which is on the other side. You're not exactly looking at the reflection of the same thing, because the square root is the reflection of this part, not of that part. And the answer that you're receiving is, again, a positive number above the axis. So this thing here is positive, while the x was negative. So they can't be the same thing. The thing can't just be equal to x, and it's not. That's why we're seeing this part here, which is not the function equal to x, but it's not something crazy and completely different either, right? It's just a reflection of that same function. So instead of being x, it is minus x. You could, for example, say that this p function, which is the square root of x squared, is equal to x for values of x that are bigger than 0, and it's equal to negative x for values of x that are less than 0. I'm writing it as a piecewise function, which is very convenient for this kind of shape. But that's not any piecewise function, is it? It's one that we've seen before. That's just the absolute value of x. So as we move on now to actually talk about trigonometric functions, which is what we all want to do, these are the things that I want you to keep in mind. There are conventions. The square root of x means the reflection of the right side of that quadratic function, because everybody decided that that's what it was going to be. But the quadratic function itself, x squared, doesn't have just one inverse function. This function here, the square root of x, is just our favorite. Out of the two that could have been, because we could also have been looking at minus the square root of x, which is this one down here. Out of those two, we prefer the positive one, and that's that. That's the convention. So keep that in mind, because something similar to that is going to have to happen for the inverses of the trigonometric functions as well. And also keep in mind that when you do a composition of a function with its own inverse, depending on who is inside and who is outside in the domain and range of the various things, usually the result is just the function x, the identity function. But when it's not, it's going to be because of things like I am using the wrong side of the inverse function. I'm using the inverse of another piece of the function, which was like the left and right of the quadratic in this example. And then the composition can be something else that is not like just y equals x, but it's not going to be something completely different. Okay, so sine of x, here we go. It has infinitely many turning points, so it is a mess as an inverse function. We are going to need a convention, just like in the quadratic function x squared. We conventioned that we prefer the right side, to invert it as the square root of x, here there is going to be a convention as well. Which one of these domains are we going to call the inverse of the sine function? And the answer is that this is the convention. This is the domain that we are going to invert in the sine function. It goes from this local minimum here, which is minus pi over 2 and minus 1, to that local maximum up there, which is pi over 2 and 1. That's for the function sine of x. And then when we do the inverse function, we are going to change the domain and the range. So instead of the range being from -1 to 1, like the sine function is, that's going to be the domain of the inverse function from -1 to 1. So this here is the point -1 and negative pi over 2. And that one over there is the point 1 and pi over 2. The function itself is the reflection of the sine function over the y equals x line. So it's that red function here. And if you want, you can imagine that the function wants to keep going like that and be periodic, just like sine of x is. But you can't do all of that in just one function because it wouldn't pass the vertical line test. So instead, we focus only on this red part here between -1 and 1 and between negative pi over 2 and pi over 2. That is the convention for what we call the function arcsine of x. People also like to use this notation of sine inverse of x. Personally, I have a slight preference for using the name arcsine. I think that emphasizes the fact that a choice has been made and this is the part of the sine that is being inverted, while when you say sine inverse of x, for me that sounds more generic, like I could be inverting any domain of the sine function. Then again, that is just my personal preference, but it's what I am going to be using. Yeah, so that is the convention for inverting the sine function. The domain is from -1 to 1, and the range is from negative pi over 2 to pi over 2. So now that's another function that you know. And I should also tell you what the convention is for the cosine function, which is this. For the cosine function, we are going to be inverting from 0 to pi, so that the point 0, 1 becomes the point 1, 0. This point here where the function crosses the line stays where it is, and the point pi and -1 goes to the point -1 and pi. Let's make sure to keep the value of the x-intercept correct over there when we do the y-intercept. So this is what the function looks like. And this function is called arccosine. The domain of arccosine is from -1 to 1, and the range is from 0 to pi. Yeah, so the interesting thing about the inverse trigonometric functions is to explore domain and range when you do function composition involving these functions. So the simplest exercises will be this kind here. Just ask you for a sine of arcsine of a value or arcsine of sine of a value. And sometimes they can try to trick you. For example, arcsine of the square root of 3. Well, that doesn't exist because the domain of arcsine is just from -1 to 1. If there was an arcsine of the square root of 3, that would mean that the sine of x is the square root of 3, because that's an inverse function, and there is no such thing, because any angle that you get here, the sine will always be less than 1. So for this first exercise, the answer is that it does not exist, because if you can't even do the inside part of the composition, there is no value of x, so you can't even ask what the sine of x is, let alone get an answer. But what he's trying to trick you into giving the wrong answer here is that, well, sine and arcsine cancel out, so the answer is probably the square root of 3. But it isn't. The second one looks better. Sine of 3 pi over 4. That is something that we can get in the unit circle. Pi over 4, 2 pi over 4, 3 pi over 4 is here. So the sine of 3 pi over 4 is root 2 over 2. And again, he was kind of trying to trick you into the wrong answer in the same way, because if you cancel out the arcsine with the sine, then you're going to think that the answer is just 3 pi over 4. But it's not, because the range of the arcsine is only from -pi over 2 to pi over 2. So it's never going to be 3 pi over 4. From negative pi over 2 to pi over 2 is angles in the fourth and first quadrant. So in these quadrants, the angle that has root 2 over 2 as a sine is actually pi over 4. So that's the answer here. And this is the kind of way in which these functions are interesting, because they are the inverses of the trigonometric functions, but they don't exactly cancel out properly when you compose one with the other. So those exercises were exploring this in specific value at a given point, but I want to see what happens to that composition as a function, just like we were doing with the other examples before. X to the power of 3, the exponential of x, and then x to the power of 2 was more interesting because it went like this. So what is going to happen in this case? Well, the sine inverse, which is the red function here, is the one that has the smaller domain. So if I put it as the inside of the composition, that is going to restrict the domain a lot. And then we get, just like we've been getting in the other examples, a composition function which is a part of the y equals x line, but it's just from -1 to 1. It's just a small part that matches the domain of the arcsine function, which is also from -1 to 1. But the sine function has the domain that is all real numbers. So if we put that inside of the composition and the other one outside, it's not going to restrict the domain, but also right now we don't expect it to just be the line y equals x anymore, because that's what we've been talking about. It doesn't cancel out properly, just like we saw for specific values at the exercise just now. And that is what it looks like. It goes up and down and up and down. The x squared was only doing it once because the domain only had to be divided in two parts in order to invert the non-invertible function there, the negative values and the positive values. But here, because this function has infinitely many turning points, we have to split the domain in infinitely many intervals if we want to do inverse functions. So when you compose each one of these intervals inside of the conventional inverse function, this is what you get. Each one of them is doing a different thing, but not crazy completely different. It's just a line with slope sometimes 1, sometimes -1, because in some of those intervals the function is increasing and in others it is decreasing. And for the cosine function, there is nothing essentially different. Arccosine of root 3 also does not exist. Cosine of 2 pi over 3 exists. Let's see where it is. Pi over 3, 2 pi over 3, the cosine is -1/2. And the arccosine of -1/2 actually is 2 pi over 3. That is inside of the domain of the arccosine function, which is from 0 to pi. So that is the example in which it does cancel out properly because the number was inside of the domain and range. And then he goes on to talk about arctangent, which we haven't mentioned yet in the video, but there really isn't that much that is new to say. If you already know what the tangent function looks like, it's periodic, it has a period of pi, it has all of these vertical asymptotes, it's also not invertible. We also need a convention to choose which one of those we're going to invert to call arctan. And it's not surprising that the chosen interval is the one from -pi over 2 to pi over 2, because that's the same one that was chosen for sine. And then this red function is what the arctangent function looks like. It is a very interesting function with two different horizontal asymptotes, one on the left at y equals -pi over 2, and a different one on the right at y equals pi over 2. The domain is all of the real numbers because the range of tangent was everybody. And the range of the arctangent function is from -pi over 2 to +pi over 2. Now, what is going to happen when we do the compositions? Well, the arctangent function has a domain that is everybody. So when we put it as the inside function, I expect to see the y equals x line with no domain restriction. And that is exactly what's happening for that case. But when I put the tangent inside, it's going to be a little different because the domain of tangent does go all the way from -infinity to infinity, but it has all of these points along the way that are not included in the domain, which are the values where it has the vertical asymptotes. So there should be gaps in the function that is the composition. And also, it's not just going to be the whole line y equals x, because I am composing back with the inverse from a different interval. So it can't just cancel out. The answer can't just be x. That's what's been happening in all of the examples. On the other hand, it's not going to look exactly like what happened with the sine function, because over there, some of the intervals were increasing and others were decreasing, and that's not happening here. The tangent function is always increasing. So what actually happens is that you get this. You get all of these points where the function breaks and stops and goes somewhere else. This is not multiple functions, okay? The whole purple thing is just one function. You can think of it as a piecewise function. One of them is the function x, the other one is x plus pi or x plus 2 pi, x minus pi. All of them are pieces of lines with slope 1. So that's kind of the simplest type of exercise that you can get about inverse trigonometric functions, and they are really good for us to talk about this, about what's happening to these compositions. But we all know that this kind of straightforward exercise, find the value of this, is not the type of question that you find in your exams. So this topic is actually very, very interesting. It's not one of those things where I'm going to be able to tell you what the typical exam question looks like, because there is no such thing as the typical question. It's not one of these topics where you will get something out of asking your teacher, how is this going to be covered in the exam? And don't get me wrong, all teachers hate hearing that question, but a lot of times it is productive to ask that question. There are a lot of topics that have a very typical type of question that if you practice enough and you're ready and you're expecting to get that kind of question, you're going to do well when it inevitably turns up in your exam. But not all topics are like that. Not all topics have that basic typical question that you absolutely must know because it is always there with very high probability. Not all topics are something that you can just practice and repeat in the exam. Other things are not about practice at all. They are just about understanding. You have to understand on a deep level how these things talk to each other, and that's what I've been trying to do in this video. But that said, I'm going to show you parts of 2 exam questions because that was all I could find really. There aren't that many of them. And this one here is the beginning of a paper 3 questions. And in paper 3, anything goes. You're never expecting to find a typical repetitive question in paper 3, just like the ones you practiced, right? But we do have something kind of familiar here, which is a composition of a cosine with an arc cosine, but there's a catch. Now this arc cosine is being multiplied by a number n before getting into the composition. The domain of the functions he wants to study is from -1 to 1, which is fair because they have to go into arc cosine first. So those are the only values of x that can do that. And paper 3 questions have lots of parts, A, B, C, D, throughout the whole alphabet. They're guiding you through a step-by-step of how to explore the situation, but I'm just going to do things here. I'm so sorry, I was looking at the wrong function. That was sine, but the exercise wants cosine. So in the n equals 2 example, the arc cosine function is being multiplied by 2, so it's getting a vertical stretch. So the domain is still from -1 to 1, but the range is now from 0 to 2 pi because it has been stretched. So numbers between 0 and 2 pi are getting into the cosine here. And numbers between 0 and 2 pi is this. It's a full period of the cosine function. Let's explore some points. When x is -1, the inside function is getting 2 pi, and the cosine of 2 pi is 1. So f of -1 is 1. What about 0? When x is 0, the arc cosine of 0, well, it's pi over 2, but it's pi when you've multiplied it by 2. So the cosine of pi is -1. You get that point over there, and when x is 1, arc cosine is 0, and then cosine of 0 is 1 again. So what's happening with this function is that as x goes from -1 to 1, the arc cosine goes from 2 pi to 0, and these are these numbers here, so the cosine goes from 1 down to -1 and then back up, something kind of like this. And then it sort of looks like a quadratic function, and then the point of some of the items in that paper 3 question is going to be to get you to prove that it actually is a quadratic function. That is not as difficult as it might sound when I say it and you're not expecting me to say it. But I'm just going to use the double angle formula. Well, it might be more convenient if we use the Pythagorean identity to turn this sine into a cosine, right? Because then we are not mixing up what we're composing. So this is what I'm getting. And remember, even though this notation here is very usual, it just means that the square is going after, right? So I'm going to write it like this to highlight the fact that in here what we have is the composition of cosine with the arc cosine. And if you think about it for a minute, you realize that you are in the domain where these things actually just cancel out. So you get 2x squared minus 1, which is a quadratic function like you wanted. There's this other question here. This was paper 2. And this time it's not exactly the same kind of thing because we are composing the arcsine with something that is not just sine. It's just a rational function. The domain that he's giving me for the function g is all positive numbers. So I hope that the range of the inside function, which I'm calling f here, I hope that that range fits inside of the domain of arcsine, which is from -1 to 1. Because otherwise I couldn't do this composition. F of 0 is -1. Function definitely has a horizontal asymptote at y equals 1 when x gets very big. And it's definitely reaching that asymptote from below. This f of x is always less than 1 because the numerator is always slightly smaller than the denominator because of the -1 or the +1 that is in the bottom. So yeah, I think it's just going to look like this. This x-intercept here is 1, kind of easy to find. It's a paper 2 question, okay, so you can plot it in the calculator and check if you want to see if the function actually looks like this. But when he wants the domain of the g inverse, that's the range of g. So we've just found that the range of f is from -1 closed to 1 open because of the asymptote. So when that interval goes into the arcsine function, it's almost everything that could go in. It's just the number 1 that is not being reached. So what's going to come out is almost the entire range of arcsine. It's just that last point there at pi/2 that is not going to be reached. Okay, but that was not the whole question. I've skipped the part where he asks to actually invert the function. That is not the kind of exercise that the calculator will help you with. So I'm just going to change the values of x and y and solve this equation for y. Of course, I'm going to start by doing the sine operation on both sides. You should get nervous when you do this, because what I did on the right side was to cancel out sine of arcsine. And I've just spent the whole video telling you that that's not always as simple as it looks. But in this case, it is correct because sine of x on the left side is going to give a number between -1 and 1. And we've already established that the fraction on the right side is between -1 and 1. So the rest of the steps have nothing to do with sine. I'm just going to do a distributive here. Moved all of the y's to the left and all of the non-y's to the right. Now I'm going to factor out a y squared from the left side, and I'm going to take the square root of that. Okay, well, good thing pi/2 was excluded from the domain, because if I put pi/2 here, then sine of pi/2 is 1 minus 1. I would be dividing by 0, so that's not good. But that's it. So let me know what you thought of all this, and also if you have any other interesting problems involving these functions. And if you like this video, I think that you're also going to like the other one where I was exploring the graphs of different compositions of functions. So I'm going to leave a link here in case you want to go see that.